Hello everyone, welcome back to my channel. My name is Aryan Uppin, currently studying in Sri Venkateshwar College of Engineering, Bangaluru, from the section HR. Today I am going to cover the topic vector integration. So let's begin. Vector integration. Agenda. Today we are going to cover the topics introduction, vector operations, introduction to vector integrals, line integrals, surface and volume integrals, lastly conclusion. So let's begin. Introduction. Definition of vector integration. Vector integration refers to the process of integrating vector valued functions over a region in space. Its mathematical tool used in various fields such as physics, engineering, and computer graphics to compute quantities like force, flux, or work which are represented as vectors. Vector operations. Vector operations are mathematical operations performed on vectors. Some common vector operations include such as vector addition, scalar multiplication, dot product, cross product. So briefly we come to know about those. First one, vector addition. Vector adding two vectors together to find the resultant vector. This is done by adding corresponding components of the vector. Second one, scalar multiplication, multiplying a vector by a scalar, that is a single numerical value. This operation scales the vector by the scalar value, changing its magnitude but not its direction. Third one, dot product, that is scalar product, multiplying two vectors to obtain a scalar quantity. It involves multiplying corresponding components of the vectors and then summing them up. Fourth one, cross product, that is vector product, multiplying two vectors to obtain another vector that is perpendicular to both of the original vectors. The magnitude of the resulting vector depends on the magnitudes of the original vector and the sign of the angle between them. These operations are fundamental in vector algebra and find applications in various fields including physics, engineering, computer graphics, and so on. Introduction to vector integration. Vector integration is an advanced topic in mathematics and physics that extends the concept of integration from scalar function to vector valued function. Enhance scalar integration deals with finding the area under a curve or a accumulation of a scalar quantity over a region. However, vector integration deals with integrating vector fields over regions in space. For example, in physics, vector integration is used to calculate quantities such as work done by a force field, flux through a surface, or circulation around a closed curve. These quantities are represented by vectors, and vector integration allows us to compute their total effect over a given region. Vector integration involves techniques such as line integrals, surface integrals, and volume integrals, which generalize their scalar counterparts to handle vector quantities. It plays a very crucial or very important role in various fields including electromagnetism, fluid dynamics, and engineering, and so on. Line integrals. Line integrals are a type of vector integration used to calculate quantities along a curve or paths in vector field. Mathematically, a line integral or a vector field can be denoted as f of x comma y comma z is equal to f1 of x comma y comma z comma f2 of x comma y comma z comma f3 of x comma y comma z along a curve C parameterized by r of t is equal to x of t, comma y of t comma z of t, where b is given by integration of f dot dr from c is equal to integration of f of r of t dot r dash of t dt to the limit of a to b. Here f dot r represent the dot product of the vector field f and the differential vector dr, which represents an infinitesimal displacement along the curve C. Line integrals are used in physics and engineering to calculate quantities such as work done by a force along a path, circulation of a fluid flow around a closed curve, or the flux of the vector field through a curve. They provide a way to quantify how a vector field behaves a specific path. Surface integrals. Surface integrals are a type of integration used to calculate quantities over surface in three-dimensional space. They generalize the concept of a definite integrals to functions of two variables defined over a surface. Mathematically, the surface integral of a scalar quantity function is given by f of x comma y comma z over a surface S. It is denoted as integration of integration f of ds from S. Here ds represents an infinitesimal area element on a surface S. The surface integral is computed by integrating the scalar function f over the entire surface, taking into the account orientation of surface. Similarly, the surface integral of the vector field f of x comma y comma z is equal to fx of x comma y comma z comma fy of x comma y comma z comma fz of x comma y comma z over a surface S is denoted by integration of integration f dot ds. Here ds represents an infinitesimal vector area element on the surface S. The surface integral is computed by taking the dot product of the vector field f and the surface normal vector n at each point on the surface and integrating over the entire surface. Surface integral are used to various fields such as physics, engineering and mathematics to calculate the quantities like flux, mass, charge of or energy flow through surfaces. They provide a way to quantify how a scalar or vector quantity spreads out over a given surface. Volume integrals. Volume integrals, also known as triple integrals, they are used to calculate quantities over three-dimensional region in space. They generalize the concept of definite integrals to functions of three variables defined over the volume. Mathematically, the volume integrals of a scalar function, that is f of x comma y comma z over a region in three-dimensional space, it is defined or denoted by integration of integration of integration of f dv. Here dv represents an infinitesimal volume element within the region V. The volume integral is computed by integrating the scalar function f over the entire volume, taking into account the shape and boundaries of the region. Similarly, the volume integrals of the vector field, that is f of x comma y comma z is equal to fx of x comma y comma z comma fy of x comma y comma z comma fz of x comma y comma z over a region V. It is denoted by integration f dot dv. Here dv represent an infinitesimal vector volume element within the region V. The volume integral is computed by taking the dot product of the vector f and the infinitesimal vector volume element dv and integrating over the entire volume. The volume integral are used in various fields such as physics, engineering and mathematics to calculate quantities such as charge, energy, fluid flow within three-dimensional regions. They provide a way to quantify how a scalar or vector quantity is distributed throughout a given volume. Conclusion: vector integration plays a vital role in various fields, including physics, engineering, mathematics. In physics, vector integrals are fundamental for analyzing quantities like force, velocity, and electric and magnetic fields. They are essential for understanding concepts like work, flux, circulation, and divergence, which are crucial in mechanics, electromagnetics, fluid dynamics, and many other areas of physics. In engineering, vector integrals are intensively used in engineering disciplines such as civil engineering, mechanical engineering, electrical engineering, and aerospace engineering. They are applied in analyzing stress and strain distribution in materials, fluid flow patterns, electromagnetic phenomena, and structural mechanics. In mathematics, vector integration is cornerstone of the vector calculus, a branch of mathematics that extends calculus to higher dimensions. It provides powerful tool for studying vector fields like line integrals, surface integrals, and volume integrals, which is essential for the to solve a wide range of mathematical problems. Thank you for watching my video.